For the top problem set, if you want to pause the video and label each as either aromatic, non-aromatic, or anti-aromatic, we can then discuss the answers once you complete them. So for A, we have this square structure and two double bonds within it. And if we follow the criteria that we had laid out before, we see that the structure must be cyclic or polycyclic. So looking at this, we see that yes, it is cyclic. There are no open areas within the structure, it's all connected. Number two, the structure must not have sp3 hybridized atoms. So we see that's sp2 because part of a double bond, same with that, part of a double bond and part of a double bond. So we cleared criteria number 2. And then for number 3, the number of pi electrons in the ring must equal 4n plus 2. So we can have 2 pi electrons, 6, 10, and so forth. Now when we have a double bond, we count 2 pi electrons per double bond. So in this case we have 2, 4 pi electrons. Now if we use the rule 4n plus 2, is there any way if we put an integer in for n that we can get 4? The answer is no. So if we put in 0 for n, we get 2. If we put in 1 for n, we get 6. So since this has 4 pi electrons, this makes it anti-aromatic. Remember, anti-aromatic satisfy rules 1 and 2, which this one does, but it will not satisfy rule 3, which is the number of pi electrons. For B, okay, criteria number 1. It's a cyclic structure, so we're good. Number 2, there are no sp3 hybridized atoms. Okay, so remember sp3 hybridized means we have 4 regions of electron density. So if this atom right here, we're going to look at it, how many regions of electron density does it have? Well, it has a region down and to the left, a region down and to the right, and then we don't have this drawn in because they don't draw in hydrogens all the time, but this is our third region of electron density, the bond to the H. And now since we have a positive charge, that means we're missing one region or one lone pair or something. In this case, it would be another bond. So this is sp2 because we only have 3 regions of electron density. So we're good there. This is part of a double bond, so that's sp2, and same with that one. So this is a cyclic structure. All atoms in the ring are sp2. And now number 3, we have only 2 pi electrons. And following the 4n plus 2 rule, we see that if we plug in 0 for n, we can get 2. So this one is aromatic. Okay, now if we look at structure C, we see that it is a cyclic structure, so that satisfies rule number 1. Rule number 2, no atom in the ring can be sp3 hybridized. Well, this atom and this atom are part of a double bond. This atom and this atom are both part of a double bond. Now up here with this atom, we do the same thing as with this atom up here. We can imagine drawing in this H. So we have one region of electron density down and to the right, another down and to the left, and then the region bonded to the H. That's 3 regions, sp2. So we're good. Now, number of electrons, pi electrons, 2, 4. Can 4n plus 2 equal 4? Well, as we saw up here, the answer is no. So this is anti-aromatic. structure D. So this time we see we have a nitrogen within the ring, which that is perfectly fine. So rule number 1, it is a cyclic structure. Rule number 2, are all atoms sp2 hybridized? Well, if you look at the ring, each of these atoms in the ring have a double bond connected to them, so we know that they're all sp2. Now we just have to count the number of pi electrons. So we get 2 from this double bond, 2 from this double bond. Now when you have an atom with a lone pair and a double bond attached to it, you don't count both the lone pair and the double bond. You're just going to count the double bond pi electrons because you can only have 2 pi electrons on one atom. So this is 2, 4, 6 pi electrons. And following the 4n plus 2 rule, we get 6 if n is equal to 1. So this is aromatic. For structure E, so rule 1, is it a cyclic structure? Yes. Rule 2, all atoms are sp2 hybridized within the ring. So this atom, those are both carbons with double bond. It's good. There and there are carbons with double bonds. Up here, so this carbon, if we draw in the H's, it has 2 H's on it. 1, 2, 3, 4 regions of electron density. That's sp3. Now, because we don't satisfy rule number 2, this is non-aromatic. Now let's look at this bottom problem. So, which structure is non-aromatic? Now remember, we have the choices of aromatic, non-aromatic, anti-aromatic. So take a couple minutes and see if you can determine which is non-aromatic. Okay, so if we look at structure A, we have 2 pi electrons, 4 pi electrons. Now when you have an atom in the ring with a lone pair on it, and there is no double bond attached to it, you can count this lone pair as pi electrons, so we'll include those in our count to get 6 pi electrons. Okay, this is a cyclic structure, so rule 1 is good. Rule number 2, all atoms in the ring are sp2 hybridized. Well, since we included this lone pair as pi electrons, that makes it sp2, because it has 1 region, 2 region, and this would be your 3rd region of electron density, so that makes it sp2. And then 4n plus 2 can equal 6 if we make n equal 1. So this one is aromatic. Okay, structure B. Now, when we look at structure B, remember for rule 1, we can be cyclic or polycyclic. This is an example of a polycyclic structure because we have 1 ring over here, and then we have another ring over here. So we know that rule 1 is good, but for rule 2, we need all atoms within the rings to have sp2 hybridization. So let's start on the right side. It's part of a double bond, same with that and that, so those are good. These 2 carbons are part of a double bond. Okay, this nitrogen here, so this has a hydrogen bonded to it, and then it also has a bond to carbon, and a bond to carbon, and then we know that nitrogen likes 5 electrons in its valence shell, so we know that there must be a lone pair here. So nitrogen right now has 1, 2, 3, 4, 5 valence electrons, no charge on it. But we notice it's sp3 hybridized. We have 1 region of electron density, 2 regions, 3, and 4. So since this is sp3, that makes this structure, or this atom, that makes the compound non-aromatic, because right now we have a non-sp2 atom within the ring. And then you could have determined the same thing if you would have gone up here. So this nitrogen, I did not draw the H in on it, which sometimes they don't draw the H's in on, so just be aware of that. And then it also has a lone pair. So using the same logic as down below, this is also an sp3 atom, and that would make it non-aromatic. And then the third place that is wrong here is that this carbon here has two H's on it. That carbon is also sp3. So 3 different spots within this ring, we can see that the aromaticity would be lost. Okay, for structure C now, it is a cyclic structure, and we see that the top and bottom carbons would have both 2 H's on them. Now because of that, we have 2 sp3 atoms within the ring. This again is non-aromatic. And then finally structure D, cyclic, so rule 1 is fine. Now all atoms are sp2. Atoms that are part of the double bond we know are going to be sp2. This one here will have an H on it. And then it has 1 region, 2 region, 3 regions of electron density. So this is indeed sp2. And then the third criteria is 4n plus 2. Pi electrons, 2, 4, 6. N can be 1. So this is indeed aromatic.